So I'll be presenting interaction between the testing and forward testing effects, implications for theory, individual differences, and applications. So pop quiz, of course, we're talking about the testing effects, so you're going to get tested, and just to troll the professors. But anyway, so the testing effect refers to the phenomenon where A, taking a break between study sessions can improve long-term retention, B, practice testing can improve long-term retention compared to simple restudying of the material, C, learning is enhanced when students are provided with detailed feedback after testing, or D, spacing out studying sessions over a long period of time can improve long-term retention. Anyone got any guesses here? Yeah. That's right. Yeah, B. That's correct. And there's a meta point to this that I'll touch. I'll come back to that later of why I would put this in the beginning. And so yeah, empirically what the testing effect looks like is this bar chart. So on the left, we have items that were restudied. In the lightest blue, and the medium blue, we have items that are tested. And so the gap between these two bars, that's what the testing effect looks like empirically. Oh, you can't see my mouse. Let me get the laser pointer. Yeah, so this gap right here between these two conditions is the testing effect. And this third bar is a prediction from a model that Tim created called the dual memory model. And so this is the only computational model that exists to explain the testing effect, and is based on some simple assumptions. So when you first study some information, you create a study memory. And then when you go to restudy that information, you strengthen that study memory. But when you test yourself, not only do you strengthen that study memory, you create an independent and identical test memory. And so just because of the fact that you have two routes of retrieval, it makes you more likely to retrieve that bit of information, which produces the testing effect. And so the dual memory model builds its assumptions at the distribution level of the memory strength for all items. So you can first look at the study memory, and this red dotted line is the initial distribution memory strength for all the learned items. And there's this T threshold. So if your memory strength is past the threshold, you'll have a correct recall. So it's a 1 or 0. And then this blue line is the distributions after that restudying has occurred. And so it strengthens the overall distribution. And so that's for the case of restudy, but with testing with feedback, it's the same case. The study memory will start out looking like this red dashed line. Then after you test, it'll look like this blue line for the study memory in the test condition. But then you'll also have this testing with feedback, and so you only generate that test memory after you've tested yourself through training, and you create an identical distribution for all those items. So now, because we have these two routes of retrieval, again, we'll create the testing effect. So what this looks like, and theoretically with equations, so using some process assumptions that are the simplistic case, that retrieval from study and test memory is stochastically independent, and where possibly empirically supported, we derived a simple parameter-free quantitative prediction for the probability of retrieval for testing items on the final test. So PT is the probability that you'll retrieve from test memory, and PR is the probability you'll retrieve from restudy or study memory. So theoretically, we can define the testing effect as the probability of getting an item correct via test memory minus the probability of getting an item correct via study memory. So we can represent the probability. Yeah. So yeah, restudy memory maybe. Yeah. Thanks for the clarification. And so we can represent PT, or the test memory, as the probability of correct retrieval via the test memory using inclusive OR equation as the sum of the study and test memories, distributions minus the product of those two distributions. And we can do this because we assume that the distributions of the study and test memory are equivalent, right? And so we can kind of swap those out and replace those values with the memory distribution strengths of the probability of correct retrieval from a restudied item. So then we can simplify that equation to 2PR minus PR squared. Yeah. And so finally, we can define the testing effect magnitude as the sole function of PR, where it's PR minus PR squared. So now, in summary, because we can assume that the memory strength distributions of the study and test memory are equivalent to the distributions of the restudy memory strengths, we can predict TE, the testing effect, as a sole function of the restudy memory strengths, because we can interchange all of them for one or another. So practically what this looks like and how we can actually predict real data, we can take the proportion correct values of the restudy condition. So that'd be like that left blue bar on that bar chart earlier that we saw for each participant to predict the proportion correct values of the test conditions for each participant. So here we're assuming that the proportion correct values are reflective of the distribution strengths of the restudy memory. That's when we can predict PCT, which is just the test proportion correct test values, and the testing effect using the theoretical equations using proportion correct. For now, if you have notes, I'll say like PCT and PCR to just denote like the proportion correct restudy values and test values. And so, do these equations actually work? They actually work quite robustly across a large amount of data sets. So here's one example of it working on 10 different experiments inside and outside of the lab. So the black bars here are the restudy conditions. So those are the PCR values. And the gray bars are the PCT values. And then the dashed line is the model prediction. So the goal is to line up the dashed line with the gray values. So overall, it does a very good job. But when you actually average this entire thing out, it's like almost spot on in this example. And this, it also works in a variety of other data sets as well, not just these 10. So it's a very robust parameter-free estimation of the testing effect. And because there are no free parameters in the model, it can make predictions for any descriptive statistic for PCT, including the cumulative distributions. So on the y-axis, we have the cumulative proportion correct. And then on the x-axis, we have the quantile or the proportion of participants at or below the cumulative proportion correct value. The red dots are the restudy values, and the blue dots are the test values, and the black line is the model fit. And so distinctively, the CDF or cumulative distribution function for PCR is much lower than the CDF for PCT. And it shows this nice gap. And this reflects how the model's prediction in the bar chart is that it follows along across the entire quantiles, all the quantiles. And so due to the model's empirical regularity and queued recall, which I'll talk about what that design looks like in a second. If it fails to accurately predict the testing effect, this could imply that either the model is wrong, or it could imply that there's a confound in the design of some types of experiments that's unrelated to the testing effect. So if there is a confound, we should be able to manipulate that variable and show that the model is failing due to extraneous unrelated confound to the testing effect. So here's an example of what it looks like when the model fails. So on the left is what we would expect, and on the right is the model overshooting. So red's restudy, blue's test, and black's test predicted, the model prediction. I think I keep those colors constant throughout the talk, so I might not say them again. So yeah, this is the expected one on the left side, and the right side is not the expected one. So again, we have on the y-axis the proportion correct. So, and then on the x-axis we have the groups. Don't worry about the group labels right now. So in the group on the right, the model over predicts the test condition, but note that the PCT values for these two groups they are statistically equivalent. They're nearly identical. But the PCR values in this group on the right side is much larger than these PCR values on this left side. So, and if you remember that the PCR values are how the model makes its predictions, so it stands to reason that there's something going on with the restudy condition, and there's nothing happening with the testing condition. So this implies that it's not something to do with the testing effect itself, but it's something to do with this restudy condition. And so we can also see this pattern bear out in the distribution. So these are from some large N data sets that are published in the literature. And so we already saw what the normal cumulative distribution looks like when it's doing a good job of estimating PCT values. And so here in each study, we're overshooting by a fair amount. This black line here is the model prediction, right? And so in each case, it's just overestimating the values of the PCT. And so one thing to note here is like up until like 0.15 in each case, it does a pretty good job of estimating it. But then after that, it's just overshooting it completely. And then another thing to note here in these conditions or these data sets is that these PCR values, the gap between the PCT values is much smaller than it previously was and that we saw. And so this, again, I haven't overlaid it yet, but this also possibly suggests that it's something wrong, not with the PCT values, or not something wrong with it, but there's something wonky going on with those PCR values that's making the testing effect smaller or causing the model to overestimate. So we're left with two possibilities. Maybe the model is systematically failing to predict certain types of data because it doesn't fully capture the mechanisms of the testing effect, or it could be that there's some third variable causing the data to behave weirdly that the model isn't built to account for, or is unrelated to the testing effect. Yeah. Yeah, well, you just asked the perfect question right in the next one. Yeah, so one of the important things I haven't mentioned yet is like what the design of these studies are. So how our lab typically designs in these studies in this way, and most labs do too, is there's two conditions. There's the restudy condition and the test condition. So when you first start, you first learn initial word pairs, so you study laces shoe. And then you go right immediately into the training phase for the restudy condition, and you study that same word pair, those same word pairs again, laces shoe. And then there's some retention interval, like you come back in the lab 2 days later and you're shown the cue word and asked to recall the target word shoe. In the test condition, you're again shown, you initially learn the information, lime salt, and then in the training condition, you're shown the cue word and then asked to recall the target word, salt. And then regardless of your answer, you're given correct answer feedback, lime salt. And then again, 2 days later, or whatever retention interval you have, you get a final test and you're shown the cue word and asked to recall the target word salt. And so in this group, the test condition will have better recall than the restudy condition in pretty much all cases. And so, so this is the general structure of a cued recalled experiment, but we can make a lot of variations on this design. And one of those key variations that we're going to talk about today is the ordering of this training phase. So this training phase, what we normally do in our lab is we randomly mix the ordering of whether an item will be restudied or recalled during the training phase. So there's some vector that might tell someone or might tell them to test this word, or restudy this word pair, or test this word pair, restudy, test. So it's randomly intermixed together, completely random for each participant. And so we're going to call this the mixed practice. Those other studies, however, that we saw earlier where the model was failing, they were doing something called block practice. So the block of tested items came before the restudied items. So we know that the model has been failing in one specific type of design, which is this blocked thing. So they'll be tested. They'll have like 40 items of testing, and then they'll have 40 items of restudy in the training phase. So that's the case. It seems like that's the case where the model is failing to actually predict. So second pop quiz. The forward testing effect is A, testing enhances subsequent learning through study. B, testing is better for learning than restudying. C, spacing out your tests will yield better retention. Or D, interleaving different types of test problems yield better retention. Any guesses? Maybe not. It's A. So, oh, did I just end the slideshow? Oops. Sorry about that. Didn't mean to do that. Okay, there we go. Yeah, so forward testing effect, testing before studying information, enhances learning or relearning of that information. So that's I had that initial test in the beginning because I'm creating a forward testing effect for you guys. So hopefully you'll remember more of what I say in this lecture. Right, so yeah. Yeah. So on the test, how we normally do it is testing with correct answer feedback. So you get feedback of what the correct answer is, regardless of you answered correctly or not. And the testing effect exists without the feedback regardless, but the feedback makes it stronger. Relearning or initial learning, but we're particularly concerned with the relearning of it. I'll get on to like why some mechanism of the forward testing effect. Like it's not super clear exactly what those mechanisms are, but yeah, we'll dabble in it. Right. So yeah. So this oddly sounds like the forward testing effect. Oddly sounds like the conditions of the blocked testing effect design, where testing will enhance the learning of restudy items during the training phase. So this one right here, you test, and then that's going to enhance the learning of these items. Whereas this one is just randomly intermixed. It should have relatively no effect. So based on these observations, we can make several hypotheses. The first is that in the designs where test first training is used, there will be the forward testing effect will be present, so it will enhance the recall of those restudied items. And so this is what will diminish the testing effect, and it will only affect the restudy condition, and the test condition will be unaffected because of this. Yeah, exactly. Yeah. Mm-hmm. And then secondly, the restudy first designs. So if you just have the restudy before the test first, or the restudied items before the tested items, this will have no FTE, no forward testing effect. And based off of a large amount of previous data from our lab and other labs, and the model's ability to predict stuff, predict the PCT values, we'd assume there's no FTE confound in mixed designs. But we ran a second experiment where we had that group, but in this first experiment we didn't have that group. So to test these hypotheses, we had a study with two groups, the test first block design and the restudy first block design. So both groups initially learned some items, some word pairs, and then the test first design were immediately tested on 40 of those random items, and then they were restudied on 40 of those items. And so this is where we think the forward testing effect is going to occur. And then 2 days later, they came back into the lab and were tested. And so we expect a diminished testing effect here. Whereas the restudy first design, they restudied first and then tested. Because there's no information for the testing to enhance afterwards, there should be no effect here. It should be a normal testing effect. They came back in the lab, were tested. And then this should be like a normal testing effect magnitude. And we didn't run this one for this experiment, but we assume that there's no forward testing effect there. But we did run it in a second experiment, because some reviewers wanted us to, so as it goes. But we'll touch on it in a second. Yeah, so you guys already saw this bar graph earlier. This was the example I gave. So in the restudy condition in red, we replicate our findings for the restudy first group. It looks exactly like a mixed training group where the model is able to accurately predict the PCT values here. But in the test first group, the model is failing to accurately predict the PCT values. And also we note that the PCT values between these two groups are equivalent, but the PCR values is much higher for the test first group. And yeah, right.
Maybe they're self-testing.
Yeah, I'll talk about the different possible proposed mechanisms. It could be a change in strategy, greater motivation, et cetera, et cetera. Yeah, and so like I mentioned earlier, the model is making its predictions based on these PCR values, so that's why it's over predicting. So this suggests. Oh yeah. Oh yeah. I think. Well, where is it? There it is. Yeah. So testing before studying information, and it's not just like any test. It can be like any test. It doesn't have to be like a queued recall test. It could be like you taking it like individual difference tests, like working memory stuff, like anything like that. Potentiate itself. I that could yeah, that's a good question of like, does it potentiate itself? I don't think that's been explored in the literature, and I'm not sure how you would disambiguate that from testing. Yeah, okay, yeah, I guess that's true. Yeah, it would, yeah. So in that way, it separates those two. Okay. Yeah. So there's like essentially like for our specific experiment we have 80 word pairs, and so 40 of them are randomly assigned to the test condition and 40 of them are randomly assigned to the restudy condition. Is that answering your question?
Yeah, but for both for the
Prior. So like here, so in the restudy condition, so okay, yeah, not in this case. Yeah. Yeah. So in this restudy first design, they do not get a test first. But we'll talk about that case actually in a little bit. Yeah, right. And so this data suggests that the FTE is present in the test first condition and not the restudy first condition. And so we can also look at the distributions as well. So the left distribution is the restudy first, and we see a nice beautiful fit here of the model. And we see this test first condition or group that has that same overfitting that we were seeing in the literature as well. And so this also confirms our hypothesis that in the restudied items the PCT values are equivalent across both groups, and is that the PCR values is what's different. So this gap is much bigger than this gap, even though the PCT, the blue dots, are equivalently in the same spots for both groups. Oh yeah, that's what I was displaying next. Yeah, so we can overlay the PCT values from both of the groups. And so the black line is the predicted values from the restudy first group, and then the black dots are the restudy first group, and the blue dots are the test first group. And so we see that the black and blue dots essentially overlay each other the whole way. And even though we are using the data from the restudy first group, the model still does a fairly good job of fitting the test first group as well. And so this further confirms that it's the PCT value or the PCR values that are getting changed. The PCT values are staying stable. So the active testing, nothing's changing there. So to summarize, we found evidence that there is a FTE present in the test first block design and not the restudy first block design. And so again, we have evidence that only the PCR is affected and that the PCT remains unchanged. And so you can make a couple of critiques of this experiment, and that there wasn't proper controls. For example, we didn't have a mixed group that I mentioned earlier. And further, we could even have a stronger control where participants only restudy items as a reference point, so we completely take out the testing during the training. And so that's exactly what we did. So we added two groups. So the test first and restudy first, those are from the previous experiment. We kept those groups in. Then we added the mixed group and the restudy only group. So the restudy only group, during training, they don't have any testing. You're just restudying all the items. If those PCT values are higher than the other groups. Okay. The metaphor testing effect. Yeah, right. So we want to replicate our previous findings, and formally we'll first see the test first group, the PCR values is greater than all the other three groups. We also predict that those PCR values for the other three groups will be equivalent, and that the PCT values will be equivalent for the three groups. There's no PCT values for the restudy only group because there's no testing. They can't have PCT values. And so let's break this graph down. So let's start with the CT values, so the blue bars for the three groups, the mixed restudy first and test first. So again, they look statistically equivalent, and they are statistically equivalent, but visually they also look very equivalent. And then we can look at the red bars. And so it seems like nothing's changing there. And we can look at the red bars for the restudy only, mixed and restudy first groups. And so those all are equivalent, statistically equivalent. And then we can look at the model prediction for these three groups. And again, the test first group, they have a higher PCR. And then we can look at the model predictions for the mixed restudy first and test first group. So we get the expected effects where the model is able to fit the mixed and free study first, and we replicate that the model is overshooting the test first group. And so then we can also look at the distribution graphs. So there was a little more deviation in the model for a couple of reasons. One, this experiment was run online. The other one was run in person. And secondly, we had smaller sample sizes for these groups as well versus the other one. I think the first experiment, they were like almost double, something like that. Yeah. But we see the same pattern. Regardless, we still see the same patterns. In the mixed training, the model does a fairly good job of fitting the data. And in the restudy first group, it also does a fairly good job of fitting the data. And again, the test first group, it's overestimating the PCT values, and largely because the PCR values are coming up closer to the PCT values, where that's not the case so much in the other two groups. So we extended our previous results from the first experiment, or we replicated those and then extended them. So we again found there's no evidence of the FTE in the mixed training. And largely, if you're using a block design only, practically speaking, if you're designing an experiment, testing first will confound restudied items due to the FTE. So now getting on to John's questions about what's causing the FTE, why does it exist? So this wasn't the purpose of the study, it wasn't to discover the mechanism behind the FTE, but we have evidence to support some of these hypotheses and disprove others. And so there's a plethora more than these four that have been proposed since the FTE was found like 2009. I don't even know how many there are now, but your bet's on number 3. All right. So it could be if you want. In the future, maybe in psych classes it will be. Yeah, so there's 4 relevant to our data specifically. And then just as an FYI, how the forward testing effect is typically researched is using list learning, not queued recalled paradigms. I think there might have been like one, but that uses a queued recalled paradigm, but just FYI. So we'll limit our inferences to the queued recalled paradigm just because we don't want to overextend. So the first is proactive interference, and it supposes, we are all familiar with this concept, so it supposes that restudied items interfere with the future learning of restudied items, where testing is proposed to eliminate proactive interference magically. And then the reset of encoding is somewhat similar, in which it supposes that resetting information degrades our ability to process future information. However, testing resets this ability to process information and make it better magically. And then change in strategy suggests that testing causes more time spent studying on restudied items and more effective encoding strategies like temporal clustering, for example, or some other things that have been proposed as well. And then increased effort just suggests that like testing increases your motivation and attentional processes that cause people to learn more during restudying. So there's been some evidence that if you take a test and you go to study some information, you'll spend longer time on actually studying that information. So like in the design of our experiments, we give people like 6 seconds to look at their word pairs, or 6 or 8 seconds, and they're definitely not looking at those word pairs the whole time. I can tell you from personal experience because I don't. So both the proactive interference and the reset of encoding hypotheses would predict that there should be some kind of FTE in the mixed groups because the tested items are interleaved in a random way. And so the restudy items for the mixed group should have a higher PCR than the restudy only group, but that was not the case. And then further, in the restudy only group, we tested whether there was a difference in recall between the first 40 items and the last 40 items, and we found no difference because both of those hypotheses would predict that the last half of the items would have a worse recall than the first half, either due to greater proactive interference or worse encoding. And so this narrows it down to 2 proposed hypotheses. Yeah, it's like yeah. So this doesn't necessarily rule out these explanations. For list learning, it just doesn't. They just don't seem to apply to queued recall as viable explanations. So this leaves us with 2 candidate explanations. The change in strategy. So possibly participants are changing how they interact with the restudy information. Maybe they're using more imaginary material or using more imagination, or maybe they're employing more testing strategies. We don't have concrete data on this or what they're actually doing, but there does seem to be some change in something, or maybe they're just trying harder on those restudied items. I don't know. Maybe it like amps you up after you take a test. I'm not sure. I mean, I guess students do feel pretty jazzed up after an exam, right? So they always feel very concerned and anxious. Yeah, so maybe that's what it is. Could be, who knows? So we can revisit these distributions that we saw on the beginning based on our experimental results, where we showed that systematically, when testing comes before a restudy, this boosts the recall of the restudied information. And so we can potentially explain why the model fails to fit these studies. In the literature, it's due to the fact that they have the testing first block design and that there's a forward testing effect confound in their data. And then we can also talk about the individual difference studies as well. So they're back in like 2013-ish. I think people were pretty interested in individual differences and the testing effect. So there's 2 studies from the literature, Brewer and, Stephen Pan, I guess it's from UCSD. But these are very analogous studies that were interested in individual differences and the testing effect. And so both studies involved working memory measures and other things that you're interested in when looking at individual differences. And the key difference between these 2 studies, there's 2 differences. But the most important is that Brewer had these tests, these individual difference tests, before they did the Q recall task. Whereas in Stephen's study, they had them after the queued recall task. Yeah. The second difference is that the Brewer study had the restudy first design, but we showed that there is no forward testing effect confound there. And then in Stephen's study, he used a mixed design. Yeah, I'm getting into it. Yeah. Yeah, so even though Brewer still had this restudy first design, he had those tests before. So this is getting to that point. It doesn't just have to be a queued recall test. It can be any kind of test that even involves no episodic memory retrieval. And these were replaced prior to the queued recall task. And we see the same for testing effect confound here, where the PCR values are higher, and then the PCT values are the same, and of course the model is overestimating. So this suggests that, regardless of what the test is, just any test can be involved. This can either increase motivation for the restudy items. It's kind of weird, hard to explain how you would change your strategy if you're doing an unrelated test to learn future items. I don't know how you would change your strategy, but maybe it's possible. So yeah. So although this wasn't like a randomized study, it's nice like A/B test that exists in the wild, that also lends itself to the story that we're making. And so we can again look at these PCR values. I accidentally switched the colors on this one, so restudy is blue now, and the test is red. And the open circles are Brewer, and the closed circles are Stevens' study. And so we see the test again, the PCT values are overlaying each other as they go up, but on the restudy values, the Brewer is much higher and much closer to the PCT values than Stevens' study. So again, showing that same pattern of the forward testing effect. And so and so this is important. So if you're interested in, looking at individual differences, you should not have those tests before you do the queued recall task. And so we can summarize this work on 5 main points. So the forward testing effect confound is present in queued recalled paradigms where testing is prior to restudy. And we can also find that the FTE confound only affects restudied items, as evidenced by the means and distributions. And proactive interference and reset of encoding hypotheses seem unlikely explanations for the FTE in the case of queued recalled testing. And then also the dual memory model predictions hold for the PCT, both when there is and is not an FTE confound. And then also the FTE may be caused by enhanced motivation or change in strategies leading to greater effort to learn and likely improved encoding strategies during restudy as well. Yeah, and so of course I would like to thank Tim, my advisor, and also Stephen for our collaborative work on this study. Yeah. Yeah, I see what you're saying. I think I understand what you're saying. So, maybe there's like, I guess you could design it where you have like 2 blocks, A and B, and then in the A block you randomly intermix the restudied and tested items, and then in block B you could remix or interleave those as well, or randomly mix those up.